Okay, we started our discussion on synchronous rectifier, right? The importance of looking at uh, replacing. You need to be able to determine whether or not you need to replace the diode in the DC to DC converter and replace the diode with switches, right? With MOSFETs, for example. Again, the objective here, as I mentioned last time, would be to improve efficiency, right? Because diodes would have forward drop, right? And as current goes through this diode increases, then the drop increases as well, right? And the bigger the drop with a larger current, the bigger the power loss on these diodes, right? So therefore, it'll be more efficient if that is the case, right? If that's the type of application that you're designing for, it'll be more efficient for you to replace these diodes with MOSFETs, right? And this is the basic of synchronous rectifications, right? So how does synchronous rectifier work? Simply by replacing the diodes with MOSFETs or with other type of switches, right? That would improve the efficiency, because if you have diode right here, this is an example using a buck converter, as you can see from here, right, from this picture. And this diode is there to provide the path for this inductor to freewheels, right, or discharge. And as this inductor is discharging, this diode introduce around 0.3 to 0.8 maybe, depending on the current, right, volt across the diode, right? So along with that current, discharging current with the forward drop, that gives you power loss, right? So it is the simplest way of designing the buck, right? Because then if you have the diode, you don't need to provide any signal to this diode, right? Because as you learned from 410, diode is an uncontrollable switch, right? So it doesn't require any control signal to turn on and turn off, right? It will turn on by itself and turn off by itself, depending on whether or not the potential on its anode is larger or higher than the potential on its cathode, right? And so if you do it this way, right, a traditional buck converter, then you only need to provide one gate signal, right, to the high side switch right there, right? And that's our MOSFET right there. If you are running into, or if you're designing a converter that has very large current and especially at low voltage out, right? We talked about it last time. Low output voltage, but high current. This current could be hundreds of amps, like I mentioned last time as well. At present, the processors that we have, the high-end processors, they're running at hundreds of amps, 400 amps and so on and so forth, hundreds of amps. So that's very large current, right? And at the same time, the output voltage is low, around, I would say 1.5 to 2.5 volts, right? So imagine you have 2.5 volts right here, right? And then you have hundreds of amps around here, and you can imagine, the drop across this diode would represent a significant portion of the output voltage, right? So that's when we know we're going to be running into efficiency problem, right? So what you do here is you replace that diode with another MOSFET, right? For our example here, right? So then you can see I got rid of the Schottky, I got rid of the diode, right? Then I replace it with another MOSFET. Now, this will definitely improve the efficiency, especially at the conditions that I stated earlier. Very low current, very low output voltage, and very high current, right? Especially again, those two conditions. You've got to have a synchronous technique or method instead of just diode. Now, if you do that, then the downside would be that you have to provide another signal, right? Because it is a controllable device, right? So you have to provide another signal. So that's the downside. right? Meaning, in order to control the signal, you need power, right? There's going to be power required to drive that MOSFET on and off, right? From the driver or from the controller, right? So you gotta be careful on how much gain you actually get, right, in terms of efficiency by losing the diode and then introducing, a controller loss, right? So if the gain is reasonable, or it makes sense for you to replace, and you calculate the efficiency gain, and if it's a good gain, then why not, right? So that's when you decide, okay, I think it will be, a good idea to replace the diode with the MOSFETs, because the gain that I had, that I'm getting in terms of efficiency will be significant, right? So, but that's complication though, right? Because now you have to introduce another circuit, control circuit, into the buck converter, right? And also when you are introducing the signal to the bottom switch, this is the low side switch, right? So we have high side and then low side. And by now you should know the difference between the two. This is high side right there, and here's low side switch. High side means the source is not grounded, see that? And here the source is at stable voltage, which is ground. And in order to turn the MOSFET on and off, the gate voltage right there has to be, with respect to ground, of course, has to be higher than the source voltage, right? Now that is simple if you have a low side, right? Because the low side, as you can see, the source of the MOSFET is always grounded. It's always zero, right? So therefore, it's easy for us to drive the low side MOSFET, because anytime you send a signal with respect to ground, right? So anytime that signal goes high, for sure, right, the gate voltage will always be higher than the source, right? Because the source is always grounded. The high side is not so, right? So the high side is not as straightforward in terms of driving it, right? Because now you have a problem here, right? Even if you send a pulse, let's say from 0 to high, right? This is with respect to ground, right? So this is your, let's say, your gate, right? Gate voltage. Then you want to make sure that at any given point where the gate signal is high, right, that gate node is always higher than the source. And this is not guaranteed, right, for this kind of situation. Why? Why not? Well, because the source is connected to, what do you call that node? Switching node. And as we learned from EE411, the switching node is actually not a stable. Well, maybe the word is not stable, but it's not a constant voltage, right? This node right here, right, depending on which switch is on, right, is going to go up high and low, right? If the switch is on, right, then this node voltage is going to be equal to Vin, right? And then when the switch is off, then this node is going to be 0. It's going to be pulled to the ground because the bottom switch is on, right? So it's not a constant voltage, right? So if this node right here is going up and down, right, like that, right, then you want to make sure that the gate is always higher than this voltage, right? And so therefore, kind of sidetracking a little bit here, for high side MOSFET, you need to use a special driver, right? It's called high side driver, right? So now you know the difference between low side and high side drivers, right? High side driver ensures that the pulse that is being sent to the gate is always larger than or higher than the node voltage at the source of the MOSFET. Okay, so if you come across that term in the future, high side driver, now you know what that driver is being used for. Any questions on this? All right, so that's one issue, right? Another issue would be, which exists even if you are using traditional buck, you will still have to drive a high side MOSFET, right? And then you can what is it? Then you can you might ask, why not use PFET? Because then PFET is going to be the opposite, right? Because then here is a stable voltage that's input, right? So that would be easier to drive, right, for PFET, because now the source is oh, what is it? Isn't it? Yeah. So it's going to be at the stable voltage rather than NFET. Well, the problem with PFET is that typically PFET is more lossy than NFET. You can go ahead and check this, right? Go ahead and check, RDS on of PFET for the same package type, just to be comparing apple with apple, right? If you look at NFET with the same package as the PFET, right, then you'll see that the PFET has more loss than the NFET, right? More RDS on. That's why you rarely see people use PFET, right? Because it's more lossy, to the point that RDS on could be 10 times larger than that of NFET. All right, so typically we want to keep using NFET for efficiency. Now another challenge, once you replace the diode, right, by introducing the signal, is that the two signals have to be synchronized, right? That's why it's called synchronous MOSFET, right? Or this is why it's called synchronous buck. Well, because the two signals, right, this is what we refer to as the synchronous FET, the low side in this case, because the synchronous FET has to be synchronized with the main FET, the main MOSFET, right? Meaning that we want to make sure that if the main switch is on or high in this case, right, then the synchronous FET is low. It has to be synchronized that way, right? Basically complementary signals. So if the top one is on, the bottom one has to be off, and vice versa, right? And that sounds easy to do, but it's not, right? Why not? Well, because we are dealing with real world switches, right? Real world switches will be harder to do so because they are associated with rise time and fall time. So it's not like you can actually get perfect, perfect, what do you call it, switching signals like that one, right? The MOSFET is going to take time for it to turn on as well as to turn off, especially to turn off, right? So as you are doing this, right, you're running into the risk of overlapping the two. Imagine if this MOSFET on the top right here is turning off, right, with fall time, and the bottom MOSFET is turning on. It's actually the opposite way. The top one is turning on because turning off because the signal is low, right? So the top MOSFET is turning off, and the bottom MOSFET at this point is turning on. Imagine if the top one has fall time, the bottom one has rise time. Then at some point of time, they're going to overlap. Very short time, right? But regardless, that overlap between the two signals means that you are turning on both MOSFETs at the same time. And you know very well that's a no-no, right? Because if you turn on both MOSFETs, as you can see right there, then you're probably going to see fire, right? Smoke, not good, right? So that's something that you want to avoid, right? So therefore, that's a complication, right? And so how do we prevent that from happening, right? Now that we know that real world switches have rise time and fall time, it takes time for them to turn on and turn off. How do we prevent the two to be overlapping? And this is what we call dead time, right? So when you are using synchronous FET, right, or synchronous topology, you want to make sure that you provide dead time, right? Very short amount of time, maybe 0.5% of duty cycle or less, right? Just enough to allow the two to go through switches to go through their transitions when they're turning on or off, right? So preventing the overlapping overlapping conduction of the two MOSFET, right? So imagine if this is the switching signal for the top MOSFET. Ideally, you want the bottom MOSFET to do this, right? Ideally. But we know that's not going to happen because, again, they have rise time and fall time. So what's going to happen here is that rather than looking like that, right? Well, actually, I'm drawing the control signal, so it's okay. They can be fast. So here's the control signal for the top MOSFET. For the bottom MOSFET, it's going to be, again, to prevent overlapping, we're going to introduce, or the controller has to introduce what's called a dead time. So something like, see if I can draw that correctly. Something like that. I'm going to exaggerate the picture a little bit here. Here. So now, as you can see, there is a short segment of time when the two are off. See that? Like this right here. And like this one right here. And like that one right there. Right? You can see that both switches are off, right? Maybe I should also draw it here. So the red color right there, that corresponds to the dead time that is being introduced by the controller. Right? So all the controller, synchronous controller that you can commercially purchase nowadays will provide you internally with this dead time. That's nice, right? That way we don't have to create our own logic circuit to do this. It's all already done inside the chip, right? Okay, so that's an important note that you have to realize is that you have to have a dead time for driving those two switches. Now, once you create a dead time, that's not the end of the problem though, right? Let me erase this. What is the next problem? Once you create the dead time, then what? Don't we have another problem? Anybody? What kind of problem if you have a dead time between the two MOSFETs?
No path for current to freewheel?
Exactly. Yes. Now we are preventing those the energy being discharged by inductor, to flow through that MOSFET, by the MOSFET, right? Now, for a MOSFET, it's actually okay, right? Why? Because MOSFET has another path for current to flow up, right, on the bottom portion, on the bottom. I'm talking about the bottom MOSFET right here, right? Luckily, every MOSFET has an internal diode right there, right? So, and that comes with every MOSFET, right? You don't have any choice there. Every MOSFET has a diode, internal diode. And here's an example of data sheet of a MOSFET, right? You can see there's a diode across that MOSFET, right? And it even tells you what the characteristics of that diode is, right? Reverse recovery time, reverse recovery charge, and so on and so forth, right? And notice that this is considered slow, right? 110 nanoseconds. And so that's the problem with that diode, with the internal diode of the MOSFET, right? It is there, so it protects the converter from not having the path during the dead time, for the current to flow during that time. So that would prevent that from the damage that you get, right? Imagine if there's no path at all, then this inductor get pissed, right? And you get a big spike right there if there's no path at all, right? If during this dead time, right, current, right, this discharging current cannot find any path, then you're gonna get a spike voltage at that node and will damage that low side MOSFET, right? And so again, luckily you have that internal diode, but that internal diode is slow. It's a PN type, so it is slow. and it takes time, right? As you already saw in that data sheet, 80 to 110 nanoseconds, so relatively slow. So that could create a problem as well. In two problems, right? We want a fast diode for this dead time, right? Because why? Well, because that's a very short moment of time. We cannot afford to have a slow diode. Like that's only like 0.5% maybe of duty cycle, right? So you want very fast diode to take over the current when both MOSFETs are off, right? So that's number one problem. Number two, even if it can handle the turn on time, right, during this dead time, this diode, since it is a PN junction diode, then it would be inefficient, right? You learn from Tuesday, we look at one of the manufacturer's data sheet of a PN diode, the IV curve of PN diode. They're not efficient, right? Their forward drop is not good per given current. So that would create, it could create significant loss if you just leave the diode, the internal diode of the MOSFET to handle the prevailing current, right? So that's another issue there, right? You will see that some synchronous buck converters or synchronous whatever, okay, doesn't have to be buck. You'll see that some of them they don't actually deal with this problem. They would just say, okay, I'm just going to leave the MOSFET there with the internal diode, and the reason why they do that because they feel like I'm pretty sure they did the calculation, and then they decided that yeah, having that internal diode is good enough in terms of efficiency hit. We can tolerate that efficiency hit. If that's the case, then yeah, you can just leave it like this, right? Don't do anything else. Right? But if let's say that this diode causes significant efficiency loss, then you definitely need to do something, right? And guess what you need to do? The funny thing is that, at least to me, is that you started off with this circuit, right? That's the traditional synchronous buck, right? And that diode is a Schottky. I could not find a picture for a Schottky in Visio, but that's how you started with, right? Traditional buck, and then you replace that with a MOSFET to make it synchronous, right? And then in order to improve efficiency more, guess what you need to do? You add that Schottky back, right? You add that Schottky back across, right there, okay? So it's funny to see that you got rid of the Schottky earlier, but now you have to have it back. But keep in mind that even though we have a Schottky back in the circuit, the function of that Schottky is different, right? So keep that in mind, okay? Very important to understand that the Schottky that you see here will take the full current, right? The full discharge current from the inductor, big current, right? For example, if the output is 100 amps, right? And let's say duty cycle is 10%. Well, let's not do 10%. Let's say 20% duty cycle, right? Then the top MOSFET you learn from EE411 will be carrying 20 amps, whereas the diode will carry 100 minus 20, that's 80 amps, right? Following the duty cycle. You see, that's a big current, right? And typically that's what happens in a synchronous buck, especially for very low output voltage, high output current. You get very small duty cycle, right? And for a small duty cycle, the implication would be that the main MOSFET, the top MOSFET will carry less current, and the bottom MOSFET will carry a lot more current. So in this case, if you don't have the MOSFET, you have the diode, that diode will carry a lot of current, right? And that current flows through this diode, right? So that's the function of this Schottky right there, right? Is providing a path for the entire 80 amps. This Schottky diode right there is different. The function is not to carry all 80 amps, right? This only conducts during that time, which is a very tiny duty cycle, let's say 0.5, right? 0.5% duty cycle. So it's not carrying the entire 80 amps anymore, but rather it's carrying 5 amps, 0.5. 0.5 is 0.5 amps then, right? So if let's say you have 100 amps again, with duty cycles 0.5, just like the previous example, then again you have roughly, well, it's roughly, no, that's not 0.5, 0.2 like before. That's going to be roughly 20 amps, going to be less because of that time. And then this MOSFET right here is going to carry approximately 80 amps, right? And so if it's if the dead time is, let's say 0.5%, 0.5%. So that means 0.5 times 100. No, not 0.5 times 100. What is that? Very tiny, right? 0.005, like that. Am I right? My math is correct. Divided by 100. So times 100. Well, that's going to be 0.5 amps. So 0.5 amps is going to flow through that diode. Okay. And then this.
Wait, on average, right? 0.5 amps?
Yeah, these are all average. These are all average values. The 20 amps, the 80 amps, and the 0.5 amps, these are all average. And I put approximately because it's not going to be 20 amps anymore, right? Because now you have 0.5 amps that's going to be split between the top and the bottom. I don't know the portion of it, depending on how the controller works. But you can see that time right there, right? That's what creates the 0.5 amps. That is taken away from the on time as well as the off time. All right, so keep in mind that Schottky diode now has a different purpose. Right now, that Schottky diode is no longer carrying large current, but rather is carrying very small current. Right, relatively speaking, of course. Right, 0.5 amps is considered big in electronics, but not that big in power electronics. And so then, the reason why it's important for me to say that because now when you choose the Schottky, right, this Schottky right here, this will be different from how you choose the previous Schottky, right? Right there. So this will be different, right? In terms of what rating though? Is it voltage rating or current rating? Anybody?
It should be voltage rating, right?
Voltage or current? It should be current, right? Voltage is going to be the same. The voltage rating of this Schottky for that time is going to be the same as the voltage rating on the traditional buck, right? You'll be seeing the same voltage, but current is going to be a lot more different, right? The Schottky from the traditional buck, for this example that I just presented, right? That's going to carry 80 amps. So you want to make sure that you choose a Schottky that can handle at least 80 amps average. Whereas this one, the same voltage rating, but current rating should be at the most, for example, 0.5 amps, right? So it's going to be a smaller Schottky. That's what I'm trying to say, right?
Professor?
Yes.
I know generally like diodes in parallel like aren't a good thing because like all the current will flow through the one with like the smaller voltage drop. Like will that be the case for, because the Schottky generally has like a lower voltage drop, right?
But yeah, this won't be a problem because we have two diodes, right? Let me do this. We have two diodes in parallel. One of them is slower than the other. Remember that the internal diode of the MOSFET is PN, but the other one that we add as an extra is Schottky. Well, so when it comes to turning on, which one do you think is going to be faster? Schottky, of course, right? So that's not going to be.
Will the internal one even ever turn on?
No, not in this case, no.
Okay, that's what that makes sense.
Yeah, so it's always going to be bypassed by the additional Schottky, right? All right. So those are some design considerations for synchronous rectifications, right there. Okay, so now you might see that you might have seen this circuit before, right? When you have a buck converter and then they replace the diode with a MOSFET, and then you see a Schottky across. Now you know why the Schottky is there. Right? Okay, that's for dead time. Okay, the Schottky is there to handle the dead time. All right, I'm going to skip this. That's just more information. Oh, more design consideration. Since typically this is high current applications, right? The most benefit you get from rectification if it has large current and low voltage, then it is not uncommon for people to actually parallel MOSFET. So more than one. So you have more than one MOSFET. Sometimes, 3, sometimes 2, right? Now, is that a good thing to parallel MOSFETs? From practical point of view, it is actually good. It's actually good to parallel MOSFETs. For the reason being, well, sorry, let me go back. From cost, of course, point of view, it's not good, right? Because you have to purchase more MOSFETs, and then you have to drive more MOSFETs. So you want to make sure that the driver for this MOSFET can handle the power to drive multiple MOSFETs in parallel. That's kind of the downside. But the upside of this is that, imagine if you have, let's say, 200 amps flowing through this bottom path, right? Well, let's make it 240 amps, right? Rather than pushing these 240 amps into one single MOSFET, right, which will give you this loss, right? I square RMS times RDS on, right? That's going to be big when you square, and this is average value, but RMS is going to be pretty close. So you're going to get some 200 amps square it times RDS on. That's going to give you significant loss, right? This is just conduction loss. Imagine the amount of conduction loss you get. So rather than pushing it into just one MOSFET, why not put parallel MOSFETs? This is common, right, to actually do in an application that requires very large current on the output. Right? So that's the upside, is that you are improving the efficiency by doing it this way, because as you know, by having parallel path, you are splitting the current, right? So when you're splitting the current, then you reduce the losses, right? So by doing that, you improve efficiency. Another good thing about paralleling MOSFET is that MOSFET has kind of an inherent thermal runaway protection. As you know, every MOSFET has RDS on, right, as given by this, and this graph right here. And the RDS on of the MOSFET is a function of temperature, right? So as temperature goes up, right, on the junction temperature of the MOSFET goes up, so does the RDS on of the MOSFET. So to me, this is actually an advantage, right? Because imagine if you have, let's say, 2 MOSFETs in parallel, right? And each of these has RDS on. And let's say that they are both the same MOSFETs, right? But as you know, even though they come from the same manufacturer, the same part number, internally, they're going to be different, right? There are going to be slight differences between the two, right? So RDS on of the first one might be 51 milliohms. The other one could be, I don't know, 49 milliohms, and junction capacitance will be slightly different between the two, right? So in real world, no 2 MOSFET will be exactly the same, right? So then the reason why having 2 MOSFETs or more in parallel is good, because again, RDS on could be different between the two, which is no problem. And RDS on is a problem, RDS on is a function of temperature. So imagine if you have 2 MOSFETs in parallel like this, and it's carrying, let's say, I don't know, 200 amps, right? And because one of them has slightly less RDS on than the other, let's say this is R1, this is R2, right? Very tiny resistance. Let's say R1 is less than R2. then initially more current will flow through the left side, right? And less through the right side. You agree? Because it has less current, right? So then, because there's slightly more current going to the left side, that would create more heat, I squared times R on this MOSFET, right? Because again, right here, sorry, not yet. So it is going to create more heat, temperature is going to rise here, and based on this curve, as temperature goes up, RDS on goes up as well. So because of that, right, because we have slightly more current flowing to the left, RDS on, as a result, will increase to the point that R1 will be bigger than R2 at some point, right? If that is the case, then current now shifted, right? From more to the left, now it's going to be more to the right. Make sense? Now, because of this, because now we have current that is more flowing to the right, that would cause this MOSFET to heat up, right? More than the left one. And that would also increase the RDS on, while the other one is cooling off, right? To the point that R2 at some point now becomes larger than R1 again. And then current now goes back to the left. More current now goes back to the left. So you can see there is a balancing action between the two, right? And that's an inherent thermal runaway protection that you get from MOSFETs, right? So that's why it is not uncommon for designers to put MOSFETs in parallel, because internally they're protected because of this RDS on varying with temperature. Does that make sense? And that is not quite the case with IGBTs. So paralleling IGBTs would be more challenging than MOSFETs because of this thermal runaway problem. Right? Any questions?
Wait, it's a positive feedback or negative feedback for MOSFETs? Like it naturally does not want to balance the current because RDS on of the MOSFET gets bigger. Oh wait, no, more current will go over to the other one, heating in that one up. Oh, I see.
Yeah, it's like a balancing act, right? As more current flows to the other one, then RDS on of this other MOSFET will go up, and then would naturally move that current back to the previous MOSFET, right? And it goes back and forth, right? Creating a balancing act, like I said.
So if that curve like had more than like a squared relationship, then that wouldn't work. Like because power is I squared R, and if the temperature increased faster than the temperature could adjust, then it would be an issue. Is that?
You mean if this is like a very steep curve?
Yeah, if it's like a really steep curve, like with temperature.
It's just important that it goes up, right? Because if it went the other way, then it would run away, right? It's just important that the relationship's negative, so that as it gets hotter, because it's using more power, the resistance becomes higher and it uses less power, right?
That's correct. Yes, both of you are correct actually. So yeah, this slope, right? I think it's what do you call it? Not steep enough for the MOSFET to be able to recover, right? From the previous condition. Right? Remember, it's initially heating up and then it shift the current to the other MOSFET. But it needs time, right, for that MOSFET to cool off a little bit before the current can switch back. So yeah, if you have a very steep, RDS on versus temperature curve, then yeah, that's probably going to be hard for the first MOSFET to recover. Right? And it will still be heating up, and it eventually is just going to be hot, both of them, right? Okay. Hopefully that answers both of your questions.
That makes sense.
All right. Okay. Let's see. Driving the MOSFETs. Nowadays, well, maybe it's still relevant. You could actually do what's called self-driven, but most of the synchronous rectification today or these days are being done by having a chip, right? A controller that can do the PWM, and so you have a controller that can do PWM and synchronous at the same time, right? So internally, it'll provide the data time. So you got, gate 1 and gate 2, and this is already introduced the data time between the two signals, right? So yeah, technology nowadays is good. When I took this class a long time ago, there was no such a thing. We have to create our own logic circuit to add synchronous, to add the data time, right? So life was more challenging back then, of course. But then now everything's convenient. You can just buy a controller that does both, right? PWM and synchronous, which is nice, right? And that's what you can get these days, right? Easily. You can get synchronous controller from different manufacturers. For isolated topology, you can still do this though. I don't know if this is still relevant. I have not actually seen somebody is using this method, but if you have a transformer, I'll tell you why. At least in my opinion, why people don't like this method. But regardless, if you have a transformer in the DC to DC converter, right, you can see we have the top side of the transformer, on the secondary side, of course. You have the top side of the transformer, the bottom side of the transformer, and the polarity is always the opposite, right? If the top side of the transformer is winding, secondary side of winding is plus, then the bottom side must be negative, right? And vice versa. If the bottom one is negative, positive, the top one must be negative. So it's always the opposite of each other, right? So why not take that into why not take advantage of that, right? Because they're always opposite to each other. Then I could make use of it by driving synchronous MOSFETs, right? For example, this MOSFET right there, Q2, is being driven by the signal on the bottom side of the transformer, whereas the bottom MOSFET is being driven by the top node of the secondary winding, like that, right? And by this, we know that, by doing this, we know that if, for example, this node right there, the dotted terminal is positive, the bottom side, but the non-undotted terminal must be negative, right? If that is the case, let's see. The top one is positive, so the bottom MOSFET will be on. Q1 will be on, right? Because now it receives positive signal with respect to ground, right? Whereas Q2, right now it's receiving a gate signal that's negative, right? So therefore it's going to be off, right? And since we want to have a complementary signals, one is on, the other one is off, we achieve that here, right? And then what if you have the opposite case? Well, same thing, right? We have the opposite case. If let's say the dotted terminal is negative now, that means the bottom terminal is positive. What do we have now? Well, negative on the top side means Q1 now is off, right? Because it's receiving negative right there. Whereas the Q2 MOSFET right now, if you look at the blue, is receiving positive signal. So that's going to be on. So again, complementary signal, right? So naturally, they could drive complementary MOSFETs, okay, or synchronous MOSFETs. Any question on this? And power-wise, you don't need a driver to drive. You don't need a separate chip to provide the power to turn on and off this MOSFET, because this secondary winding will give you the power, right? You can get it from the source, from the primary side. So if you need power to drive this MOSFET, that power comes from the source side, or comes from the primary side of the transformer, right? So that's convenient. But can you tell me reasons why? It's already there. It's right above it. I was going to ask why it is not common to do this method. So that's the answer, just right above it. Right. Problem is we have parasitics, right? We have parasitics in the components, including in the transformer. You have leakage inductance, you have parasitic capacitance, right? The one thing that you rarely see in the capacitor model is this. There's actually capacitance between primary side and secondary side, right? And that parasitic capacitance, people don't usually draw that because that's tiny, right? And for low frequency applications, it doesn't really matter, right? Because it's going to be open. Remember, 1 over omega C, right? So if C is very tiny already and omega is very low, then you get basically big impedance, right, across that. And so it doesn't matter at all. But then if you keep increasing omega, right, like in power electronics, especially in RF, that's even worse, right? In RF, gigahertz stuff. But even in power electronics, as you are increasing switching frequency, right, that omega increases, that would introduce leakage current between primary side to the secondary side and vice versa through that capacitance, right? And the effect can also be in terms of resonance, right? So if that L couples with is coupled with your leakage, the leakage inductance, then it creates spikes, creates the resonant, ringing, right, on the primary side, which is then reflected on the secondary side, right? So all kinds of noise problems, right, if you are using this method. And that's probably why not many people use this method, or at least I've not seen somebody using this. But it's still good to know, just in case you're it's okay, it's acceptable to use this if the environment is low noise, for example. Okay. Any question on this? Okay, so that's self-driven synchronous MOSFETs. All right, I think this is the last part of the chapter, right? Selecting MOSFETs for improved efficiency. Okay, so strictly this is between the main MOSFET and the synchronous MOSFET. There you go. So let's just use, for example, our buck converter. We have the top MOSFET and the bottom MOSFET, right? Like that. There's your V in. Right, there's your switch 1, let's call it, and this is switch 2. Right now, typically people use, as I said many times already, typically people would use synchronous buck, for example, when the output voltage is small, let's say 1.5, right, and at very high current, let's say 400 amps or something like that, right? And let's say the input is 15 volts, right? To make it easy. So you get 15 volts to 1.5. That's 10% duty cycle, isn't it? So duty cycle is 10%. You agree so far? If that is the case, then what does these, practical implication, right? We are learned by doing school. Let's discuss real world implications of this, right? How does very small duty cycle affects the operation of our buck converter, right? Especially at this condition right here, right? So coming from car poly, you should know how to think this through. Okay, so what does it mean, 10%? Right, so I would say 10% duty cycle means, we learned from EE411 that 10% means that the main switch, S1 right there, will conduct 10% of time, right? And S2 will conduct 90% of the time. You agree? Well, 10% of time means 10% of the output current. 10% of 500 amps, that's 40 amps, right? And of course, S2, roughly, of course, right? I'm not including that time right now. 90% of that would mean that you have 360 amps flowing through the bottom side. That's the first implication, right? Now we know that the top MOSFET S1 is carrying a lot less current than the bottom MOSFET. You agree with that statement? So that's the practical implication of this, of having small duty cycle, is that the top MOSFET is conducting much less than the bottom MOSFET. Okay, number two. Okay, what is number two? Oh yeah, number two. 10% means that 10% of time S1 is on, right? So 10% of time is on. And then for the bottom one, 90% of time is on, right? That means, right, again another practical implication of this is that most of the time, roughly 90% of the time, this means 90% of the time, the top switch is off. Whereas on the bottom switch, only 10% of the time, the switch is off, right? So off means what? Off means the switch is waiting. It's just idling, right? Or just waiting there and doing nothing, basically, right? It's just sitting there doing nothing, right? So imagine if this is the case, if this is the example that we have, if this is the application that you have, right, to design, 90% of the time that S1 is just sitting there doing nothing. When I say doing nothing, keep in mind that every MOSFET, this is why I said that we need to know the practical implication of this. Every MOSFET has output capacitance, COSS. You can actually find that value in the data sheet, right? Go ahead and look at data sheet of any MOSFET. It will tell you what that output capacitance is, COSS, right? So right there, you have capacitance across that MOSFET. By sitting there doing nothing, that means we are charging that capacitance for a long time, yes? You agree, right? So that's the implication, whereas the bottom one, it has the same capacitance, right? The same, not the same, sorry, it has output capacitance as well. But that output capacitance, is not is not dominating, right? Because it's 90% of the time is always conducting. So only 10% of the time we are charging that capacitance. Okay, whereas the top MOSFET, 90% of the time we charging that capacitance. So think about the energy that we store in the top MOSFET. Right, that we are storing in the output capacitance of the top MOSFET compared to the energy that we are storing in the bottom capacitance of the bottom MOSFET. 1/2 CV squared times F, to be exact, right? That's power, sorry, energy is 1/2 CV squared. Right there, right? Okay, and then if you want to do power loss, it's actually F. Right there, right? And so, how do we select the right MOSFETs then? Now that we know the two real-world implications of this example, which is a common example for synchronous buck. Right? You have high current, low voltage, right? So number one, again, is that the bottom switch will conduct more than the top switch. Number two, the top switch is waiting for a long time, for most of the time, compared to the bottom switch, right? Okay, so then the next question is, okay, how would that information be useful? Well, conduction means current, right? Whereas waiting means capacitance, right? Like I explained earlier, right? So as the MOSFET is conducting, right, that current will be seeing the same RDS on, right? And so the higher the current going through that MOSFET, the larger the loss, right? What kind of loss are we getting from conducting MOSFET? I square RMS, right, times RDS on, right? So the larger the current that goes through that MOSFET per given RDS on, the bigger the loss, okay? That's the implication of conduction. So out of the two, S1 and S2, which do you think should have a lower RDS on? Anybody? Which of the two? S2, right? S2 must have lower RDS on than S1. Why? Because S2 is carrying a lot more current than S1. You agree? All right. Now, does that mean that, how do I get to the second point? Let's see. Does that mean that it's okay for you to use the same MOSFETs for the top and the bottom? Well, we'll see, right? Because if you use the same RDS on for the top and the bottom, then the top MOSFET is carrying less current anyways, right? 40 amps. You see that? That's a lot less than 360. So having the same RDS on is probably not bad, right? Because it's going to conduct, what do you call it, little current anyways. So the amount of loss from the top MOSFET will be small, right? Because again, it's much less current, okay? So imagine if S1 is equal to S2 in terms of RDS on, right? To me, this is okay. This is fine. You agree with that? However, we have a problem. You see, this is a practical problem that hopefully, I don't know if you've heard this before, but if not, this is the first time you heard it on this class. Is that the real world issue with practical issue with this is that yes, having the same RDS, having the same MOSFETs for the top and the bottom MOSFET will be okay, except, right, now you're going to be running into the issue of the following. We know that for the bottom MOSFET, you want extremely low RDS on, yes? You agree with that statement, right? So if you pick the same MOSFET for the top one, that means both of these S1 and S2 will be low RDS on, because they're the same MOSFET. Again, that should be fine. Right? But the problem with this is that low RDS on is a dilemma, basically. Is also low RDS on also means that the MOSFET will have high COSS. Right? That's not good, right? Now, if you go back to the point that I'm making before, if you, let's say, choose the same MOSFETs, low RDS on for both S1 and S2, from conduction loss point of view, you're okay, right? But then we have problem with S1, because if you choose low RDS on for S1, then unfortunately, if you buy a low RDS on MOSFET, the capacitance, the output capacitance of that same MOSFET will be high. Right? The reason being, low RDS on means bigger package, and bigger package means bigger capacitance. That's why they're always opposite of each other. Right? If you buy low RDS on, you can verify if you don't believe me. If you buy low RDS on, then the output capacitance will be high. And if you look for high, if you find high RDS on MOSFET, then the output capacitance is actually low. So it's always the opposite. It's always the opposite, right? Because high RDS on MOSFET means small package, right? Small package means low capacitance. So it's always the opposite, right? So that's why choosing S1 equal to S2 is probably not wise for this type of application, right? Why not? Because as we know, S1 is waiting for 90% of the time. And so if we have big output capacitance, then imagine the loss that we get from S1. Not conduction loss, but switching loss. Or in this case, gate loss, Okay? So that's why I have this equation up here. Oh, sorry, it gets crowded now. I'm just gonna erase this. Right, that's why I have this equation right here to show you that we have this equation right here. I'm just looking at two losses. Conduction, here's the conduction, and gate drive, right? So you can see that for the high side MOSFET, right, so P high means loss from the top MOSFET S1. We have conduction loss that is low, so this is going to be low. Why? Because it's carrying a lot less current, but we have a more dominant gate loss, right? Because it's waiting for most of the time, 1/2 CV squared times F, right? So the second term right there for the top MOSFET is more dominant than the first term. The gate loss is more dominant than the conduction loss. Whereas if you look at the bottom MOSFET, right there, is the opposite, right? Let me erase this. For the bottom MOSFET, the more dominant loss is the conduction loss. Why? Well, because it's carrying a lot more current. Right? That's why it's important for you to pick. Oh, sorry. And the driving loss, the capacitance loss is not much for the bottom MOSFET, right? So therefore, if you look at the two losses again, since the top MOSFET has a more dominant loss on the output capacitance coming from the output capacitance, therefore it is wise to actually choose the top MOSFET to be a MOSFET that has low output capacitance. Does that make sense? So the top MOSFET, choose a MOSFET that has low output capacitance, because bigger RDS on doesn't matter. Remember the downside, right? If you choose low output capacitance MOSFET, then RDS on is going to be big. But in this case, it's fine because the current is not much anyways. Right? So that's how I would select the top MOSFET. I choose the one that has small output capacitance. For the bottom MOSFET, I would choose a MOSFET that has very low RDS on. Why? Because it's carrying a lot more current, right? And it's not much on the weighting portion of the MOSFET. So you can get big output capacitance, no worries, right? Again, that's what you get anyways by choosing low RDS on MOSFET. At the same time, that same MOSFET will have relatively big output capacitance, which is okay, right? In this case, it's fine. Okay. Does that make sense, or is that confusing to you? So that's how I would choose the two MOSFETs. Any questions? No? No questions? All right. All right, if there's no question, we are done with this chapter. All right, I think that's all I need to cover for the design consideration of synchronous rectifier. All right. If there's no questions, then let's move on to our next chapter. I've decided to not go to the next chapter, but rather skip ahead to the very last chapter. So let's see. We have snubbers, we did that. Soft switching, we did that. And then we have synchronous. And then instead of doing high voltage DC and facts and power quality and harmonics, I'm going to skip ahead to inverters. So I think it's more relevant for, goodness, it's more relevant for most of you than the other topics. Right there, multi-level and three-phase inverters. Okay. Okay, so I'm going to start covering this. We are done at, is it 1:30? I mean, I forgot now. Okay. Okay. So we have about 10 minutes. So I'm just gonna maybe spend 5 minutes just to introduce you to multi-level inverters. All right. All right, here. So in EE411, we learn about square wave inverter, right? Square wave inverter is the simplest type of inverter. You convert DC to AC, right? The basic one is that the output looks like this. Oh, sorry. The output looks like a square wave right there, right? That's the simplest inverter, right? This could be plus VDC or plus half of VDC, depending on the topology. If you use full bridge, plus VDC. If you use half bridge, it's going to be 1/2 VDC to minus 1/2 of VDC, right? And then we also learned the second type called modified square wave. That looks like this. So we create some discontinuity in the output voltage. This is the same thing, VDC to minus VDC, right? Now, the problem with the first one, the simplest inverter, is that there's too much harmonics, right? How do we know? Well, keep in mind or recall from EE411 that our objective is to have an output waveform that's shaped like a sine wave, right? The closer the output shape from to a sine wave, the better it is, right? The further away the shape to the sine wave, the more harmonics you get in the waveform. Harmonics means noise. Harmonics means losses, right? So just bad things from harmonics, right? And so that's the real problem with the first inverter, right? Too much harmonics, too much loss, right? So then to improve that, you see, we use modified square wave. This is called modified square wave, right? Modified square wave inverter. Modified means I'm creating that 0 volts across the output, just 0 segments, just like you see there. What is the purpose of that? If you remember from EE411, well, the purpose is to be able to lock into a certain harmonic numbers and get rid of that harmonics, right? Because the harmonics of the square wave is actually predictable, right? You can actually know where the locations of the harmonics are, right? The first one is number 3. That's the biggest one. And then number 5 is always odd, right? Odd harmonics, 3, 5, 7, 9, 11, and so on and so forth, right? 3 will be the biggest. And so if you would like to get rid of harmonics number 3, right, then you could actually do that. You can eliminate not just harmonics number 3, but also multiples of 3. So 3, 9, 15, they're odd, right? Odd multiples of 3. How do you do that? By introducing alpha. I don't know if you remember that, right? And the equation is 90 degrees over, I forgot, n. Yeah, right there. Right there. That's the equation for alpha. So alpha is equal to 90 degrees over n. N being the harmonic number that you want to get rid of. So if you want to get rid of harmonic number 3, third harmonics and multiples of 3, then alpha that you apply to that modified square wave would be 90 divided by 3, that's 30 degrees. So this alpha right there would be 30 degrees, right? On both sides, left and right, 30 degrees, right there too, all right? So that's just a refresher from EE411. So that's what we get from modified square wave from EE411. But still the same problem lies, right? Which is what? If you look at this waveform, does it look at all like a sine wave? Not to me, right? So that means it is still contains lots of harmonics, right? Yes, we can get rid of some harmonics, but still the level of harmonics still quite significant. So that's not good, right? So how do we improve the quality of this waveform to be closer to a sine wave, right? We could do that by using what we call multi-level inverters. However, before I go there, what do you think is the advantage of, I know I've just talked about the bad things out of this inverter. What is a good thing? What is the advantage of using this inverter besides being simple? Anybody remembers from EE411? What is the advantage compared to PWM?
You have quite a few less harmonics, right? You're closer to having a 60 hertz sine wave than if you were to you need less filtering, right?
For this one, it's going to be quite the opposite. You're gonna need heavy filtering for this because the harmonics are going to be very close to 60 hertz. Whereas PWM, the harmonics are located away.
Oh, they're further. Okay.
Right. Yes.
That's loss.
What do you mean by loss?
Like they're more efficient.
No, they're not more efficient, but the this type of inverter has better loss in terms of blank. Yeah, I'm not going to give you the answer. It has more loss because of harmonics, but actually compared to PWM, it has less loss with respect to, but there are different type of losses, right? If you look at harmonics losses, this is going to be big.
Oh, switching losses.
Very good, switching losses, yes. Because this inverter utilizes not much switching, right? It's only 60 hertz switching. There's no high switching here. There's no high frequency switching. Whereas PWM, as you learned from EE411, uses a lot of switching, right? It has a low frequency and very high frequency. So the problem with PWM is that you can run into significant switching loss, especially when the application calls for very high voltage, right? That's why for high voltage applications, people don't like to use PWM because there's a lot of switching, right? Imagine if you have to switch you have to turn the switch on and off from 0 volts to, let's say, 12,000. Imagine the loss, right? That's why
you should just do low voltage and then use a transformer after the inverter.
Then you run into a loss from the transformer, right?
Oh.
Which is not good. That's actually going to be worse, right? So that's the benefit that you get from these square wave, is that the switching loss is very small, much smaller compared to PWM. Harmonics loss is big compared to PWM, but the advantage is that the switching loss is much less because there's no switch. I mean, there's switching, but it's not much, right? 60 hertz switching, right? So then how do you improve, right? If we like to use this because it's using a lot less switching, how do we improve the shape of the waveform? That's what multi-level is, right? And then I'll spend maybe 2-3 minutes and I'm done. This is one way to improve the shape. So we're focusing on the shape of the output, right? Rather than a simple square wave, I could make it more looking like a sine wave. How? By using 2 different square waves. Imagine if I have 2 square waves just like this, right? Different alphas, right? So the first one is like this one. The second one is this square wave, and as you can see, both have different alphas, alpha 1 and alpha 2, right? Now watch, this is cool. Go ahead and add them. If you add them, what do you get? You get this. Looks like magic, huh? If you add them, look at the shape. Now we're seeing more sine wave-like, right? You agree? By having 2 square waves, you add them together, you get more sine wave shape on the output. Imagine if you have more than 2 to add, then you get multi-level. This is why we call multi-level, because there's a lot of levels there. Imagine I have more step, right? More step, like that. Imagine that, right? So then you can see it becomes more and more like a sine wave as you increase more levels, right? You see that? So if I draw the envelope with the red, right, with the more steps like that, you can see we have, actually there's more step right here too. I forgot about that. Oops, sorry. Something like that. So you can see the shape now mimics more like a sine wave, right? So this is the basic behind multi-level inverters. So if you hear the term multi-level inverters, you basically have a bunch of square waves added together, right? Of course, I'll talk about it next week. You're not going to use multiple DC sources. There's a way to do it, which is cool. I'll show you next week. You're still using the same one DC source to actually create multi-levels, right? By using switching. But the point is here is that you could improve the quality of the output waveform of a square wave by introducing more levels. Does that make sense? Hopefully. And by doing so, you're pushing harmonics even away from 60 hertz. So you're going to get filtering requirement that's even less and less and less, right? So for utility level type of inverters, they use this technology, right? Imagine the number of levels that they have to create a lot more than, of course, what I'm seeing here, that I'm putting here, right? For example, 48 levels. Imagine if you have 48 level inverter, 72 level inverter. Imagine the shape of the sine, the shape of the output voltage you get. It's going to be looking almost like a sine wave, right? The more levels you introduce. I'm going to stop right there. But is that clear? The basic behind the concept behind multi-levels? That's the objective, is to be able to mimic sine wave more by introducing more levels.